So the first kind of force problem that we're going to work on are problems where you have a system that's in equilibrium. An equilibrium just means, oh, you can't quite see it. There we go. It means the system is in equilibrium if the total force acting on it is zero, or another way of saying that is that all of the forces balance out, so it's getting pulled equally in every direction. So you actually end up being this thing called equilibrium. And objects that are in equilibrium can do one of two things. The first thing they can do is they're at rest. And students usually get that one just fine. The other thing that you see an object in equilibrium do is that it's going to be moving at a constant velocity. Forces cause accelerations, which we'll learn in a later video. But if there's equal or balanced forces, it doesn't mean that the object's not moving, it just means that it's not accelerating. So there, now that we got all that, I'll tuck myself up. Oh, sorry, I still can't quite see those words. But anyways, so that's a system in equilibrium, and I'm going to show you what that looks like on a free body diagram. And then I'm also going to show you a new thing called force equations that will prove it in a different way. So the object that we care about is going to be this object right here, this box that's getting pushed on by, I don't know, sweaty guy. So let's highlight the contact points. We have contact on that edge and contact on that edge. So we can create our free body diagram. And let's, the length of the vectors is really just a personal choice. You can kind of draw whatever lengths you want. But I know it's going to have the force of gravity acting on it. Every object on Earth has the force of gravity acting on it. And it would be unreasonable to say that this thing isn't on some kind of planet as he's pushing it across the ground. Maybe not Earth, but probably Earth. So if we have the force of gravity acting downwards on it, we can see that there's also a contact force on the bottom, the contact force called normal force that's going to be pushing it upwards. And you'll notice that I drew those vectors with the exact same magnitude. That's on purpose because I want to represent the fact that this object doesn't have an unbalanced force vertically, which means it's not accelerating up and down. In this case, it's at rest relative to the vertical direction. Then it's being pushed. We also have the push acting on it. And I don't know how that force of the push compares to the force of gravity and normal force. I'm not really given that information. So I drew it a different length because while I don't know how long it is, it's unlikely that or how strong it is, it's unlikely that it's exactly the same as gravity. So I just drew it a different length to represent that. And if this was done, if we were done drawing this, then this object is not in equilibrium because it would be accelerating in this direction, in the direction of the unbalanced force. So there's one more force, and we accounted for the contact force there. We accounted for normal force there. We accounted for gravity outside. But surfaces can create one other kind of force, the force of friction, and that's the one that we've got that's balancing this out. We also have the force of friction. And so now that we have that, it's all balanced. Okay, while it was paused, I put in the full description of those forces. 3 of them are contact forces, 1, 2, 3, and then we have the field force right here. Oops, by the Earth. So now that I've got that, we can see what a system in equilibrium looks like on a free body diagram. But there are also these things called force equations. When we're writing this out, we can write things out like the sum of the forces. This symbol right here is a mathematical symbol that just means the sum of the stuff that comes after it. So this is the sum of the forces is equal to 0 if it's in equilibrium. And I'm telling you that this system is in equilibrium, so that's how we know that this one is. But we need to, same thing that we did in projectile motion, we have to do here. We actually can't do a problem in 2 dimensions at once. So I'm going to write a sum of the forces in the x equation and oops, that's ugly, a sum of the forces in the y equation. So the horizontal forces, well, actually, before I even start this, I need a coordinate system. So I'm going to say anything going that way or going that way is positive. So now that I did that, I can start setting these up. In the horizontal direction, I have my force of push as a positive force. It's positive because it's going in my positive direction. And then taking away from that, I have friction. And I'm saying that if they're in equilibrium, those both have to be 0. And then in the y direction, I said up was positive, so I would have normal force minus mg, and those also equal 0. So this is what a system in equilibrium looks like with force equations. They're both adding up to 0. And this is what it looks like with a free body diagram. So let's do some example problems. And we'll also be doing some actual math as we go along here. So the first problem that I have, we're going to try to find the normal force acting on this guy. He's just standing there. He's not doing anything, but he has a mass of 65 kilograms. So we're gonna try and solve and find what normal force exists between him and the ground. Let's draw a circle around him, identify that there's only one point of contact, the contact with him on the floor. No reason to think there's any friction acting up here because he's just standing there. He's not trying to move. So then when I'm drawing my free body diagram, I'm gonna have a force acting downwards and a force acting upwards. This is the force of gravity, and this is the normal force. Okay, I paused it again just so I could throw in the extra labels. Let's set up the force equation though. This, even though this is still a sum of the forces equation, I can kind of skip past. Well, okay, the sum of the force is going to be 0 because he's not moving; he's in equilibrium. And in the y direction, it's the only direction that matters for us. If I define upwards as being positive, then we would have normal force minus mg equals 0. And that means, if we go to the next step, that means that normal force must be equal to m times g. We just added mg to both sides. And since mg is the mass times the acceleration due to gravity, that would be 65 kilograms times 10 meters per second, which gives me 650 kilogram meter per second, which is the same thing as 650 newtons. And that's the answer to this particular question. So we've answered that one. It was 650 newtons. Newtons are the units of forces. It's just a combination unit of the mass and the acceleration. Now we're going to find the tension on these objects. I'm going to call this is mass 1, this is mass 2. So here's a dot for mass 1, here's a dot for mass 2, and each one of them, I guess I should go through here, draw a circle around them, only has one point of contact. It's that tension pulling them upwards. So we can assume that the system is in equilibrium. It has equal masses on either side. So whether it's moving or not, it would still be in equilibrium. And so when I draw the free body diagram, I'm just going to say, okay, there's a force of gravity acting downwards on each. This is m2g, this is m1g. And then there's a force acting upwards on each. That's tension. We know that these have to be the exact same length because the system's in equilibrium. We know that these have to be exactly the same length because they're the same masses, which actually means that these also have to be exactly the same. We'll actually just explain why that is in a few days. But going through here, if we wanted to, we could kind of skip past for these problems the force equations, although we'll use them lots more going forward. And we can just say that, okay, M1 is 5 times G is 10. So this is 50 newtons there. This is also 50 newtons there. So if it's in equilibrium, this has to be equal to 50 newtons, and this has to be equal to 50 newtons. Okay, our last problem are these tension problems where we have this box that has a rope here and a rope here, and then it's getting pulled that way, which is pulling it higher and higher. And you can see that like eventually we pull it so high that, well, this is pulling that way, that one's pulling that direction. So the question is, what's happening to the tension as these go through here? And I'm going to illustrate these with free body diagrams and then just kind of explain it because I definitely don't have the room on the page. So on this one here, we would have the force of gravity pulling downwards on it. Okay, great. Which means this tension, we'll call this rope A and rope B. We'll say that that's tension A, and tension A is acting vertically, tension B goes off to this side horizontally. So tension B can't do any vertical forces at all because the force in a rope always is parallel to the rope. So you can see that it's already in equilibrium. That means that tension B actually equals 0 in this case. Because it's already in equilibrium, the box is holding up on its own there. And if I tried to put a force off to the side, it would actually already be pulling that direction. So at this moment, tension B is 0, tension A equals mg. Then as I go a little bit further though, well, mg hasn't changed because it's still the same mass. But now I'm starting to pull tension A off to an angle. And so that means now I need some tension B to handle the horizontal forces while tension A still supports the vertical forces. But because that happened, tension B got bigger, but tension A also had to get bigger because it has to be big enough to hold up mg, but also big enough to pull against tension B. And then finally, when I get to this scenario here, well, let's keep mg the same way it is. If I wanted to make this force bigger, I still have to have an upwards component on tension A. It still has to do this much vertical force in order to going upwards in order to offset the force of gravity. So if you start pulling harder and harder in tension B, the system actually, those ropes are going to pull harder and harder against each other, but tension A is still holding it up. And eventually, we're going to get to the point where tension A will snap. Because not only is tension A pulling against gravity, it's also pulling against tension B. And so if we drew a graph, it would just start increasing towards infinity, but it would never get to infinity. It would obviously break first. So there's some applications of equilibrium problems. I'm hoping this all helped you guys out.